Hey guys, today we're going to be talking about topic 5 of IBHL Computer Science Abstract Data Structures. Our focus today is going to be on linked lists, and we're going to cover points 5.1.11 to 5.1.13, which are all about dynamic data structures and how linked lists operate logically and visually. So let's get started. Linked lists are one of the most common types of dynamic data structures, and in this video we're going to be looking at how they're structured, how they work, and how we can represent them both visually and in pseudocode. So firstly, what is a dynamic data structure? A dynamic data structure is one that allocates memory at runtime, meaning it doesn't need to know its size ahead of time. This gives it the ability to grow or shrink as needed. This is different from a static array, where the size is fixed once it's created. If you need to add more data than the array allows, you're stuck, or you need to manually resize and copy it. A linked list avoids this by allocating memory for each node separately, and then connecting those nodes together using pointers. That's why linked lists are considered dynamic. They're flexible and efficient, especially for insertions and deletions. So here we can see in a fixed array it's static, but a linked list is growing, which is what makes it dynamic. Now we're going to look at a singly linked list. Each node in this list has two components: the actual data and its pointer. The list starts with a special pointer called a head, which is this thing here. Every node points to the one after it, and the last node points to null, meaning it's the end of the list. In a singly linked list, you can only traverse forward, and there's no way to move backward unless you create a more advanced structure, like a doubly linked list. So to recap, it starts from the head, each node has a data and a pointer to the next node, and the last node points to null. So now we're going to be looking at the pseudocode and a visual diagram of inserting into a linked list. We can define a function called insert, which takes three inputs: the head of the list, the value we want to insert, and the position. If we're inserting at the start, we just link the new node to the head and update the pointer. Otherwise, we loop through the list until we reach the correct position, and then we adjust the pointers. Make sure to pay attention to the base case, which would be inserting at the head, the loop for inserting anywhere else, and updating the links in the correct order. So let's see what this would look like. Supposedly we had a linked list that looked like this: A, C, and D, with this pointing towards null. And we want to insert the node B between A and C. So what will happen is we would change the pointer of B to point towards C. So now we would have A pointing towards C, and we would have B pointing towards C. Now what we would do is update the pointer for A for it to point towards B. So then it would look like this: A pointing towards B, and B pointing towards C as we had changed before. And C pointing towards D, with D pointing towards, pointing towards null. So this is how it would look like if you try to insert a node in the middle of a linked list. So now we're going to look at a doubly linked list. Here, each node has a pointer to the previous node, the data, and a pointer towards the next node. This means we can now move both forwards and backwards through the list. It's useful when we need two-way navigation, like browsing backward and forward in a history list. The trade-off is that it takes more memory, since every node needs to store 2 pointers instead of 1. But in some cases, the added flexibility is worth it. So this is what it would look like. We'd have the head, as we had mentioned before, which would be A. The head would point towards null. It would have a pointer going there and back. And then it would also have a pointer pointing towards the next node, which would be B. And then the tail, which would be C, will have a pointer towards null and going back. So to recap, it can traverse in both directions. It needs more memory to store each node, as now we have to store 2 pointers instead of 1. And it can be used in places like browser history or redo. Now we're going to look at the circularly linked list. In this version, the last node doesn't point to null. Instead, it points all the way back to the head node, creating a full loop. So here, A would be the head node. Circular lists are useful when you need continuous travel. For example, in round-robin scheduling, once you reach the end of a queue, you just wrap around back to the beginning. They can be singularly circular or doubly circular. The difference is just whether each node has 1 pointer or 2. So it would have the last node pointing back to the head, no nodes pointing towards null, and it'd be common in round-robin systems. An example of this could be if you were playing Uno. Once you go around the circle and it reaches the last player, the game doesn't end. You go back to the first person. So just a few reminders. You need to know what dynamic is and why they are dynamic. You need to know what makes linked lists dynamic. Understand how nodes link using pointers. You need to be able to draw 3 different types of linked lists, which are singly linked list, a doubly linked list, and a circular linked list. You need to be confident in writing or tracing basic pseudocode, especially for insertion. This wraps up 5.1.11 to 5.1.13 on linked lists. In the next video, we'll be looking at binary trees and how they operate logically. Bye-bye.